will use this gradient as our descent direction. So the parameters at time t plus 1. So at the beginning, I will be at time t equals 0, and I must initialize my parameters. And the parameters will be initialized by calling the initialization method in the modules. Then I will do one step. I will ask to the model, compute the forward, backward, provide me a gradient, and this optimizer will do the parameters at time t minus eta. Eta is a learning rate or step size. And I will multiply this learning rate with the gradient. It's only a scaling of the gradient, so that I can be sure that the gradient is not too long, because maybe my linear approximation will not be valid if the step is too long. So we will be using this step size. It's a hyperparameter that usually we need to fit ourselves. We can try to use hyperparameter tuning to fit this learning rate, but from my experience, I can find good values pretty easily by doing several experiments quickly, just at the beginning of the learning. So it's a hyperparameter. So let's see, we just created this algorithm. It's a valid algorithm, and we will see how it performs on our quadratic function, which approximates what is happening around the local minimum. So here it's the parameter space, parameter 1, parameter 2. My loss function are represented by the contour level curves. And I'm starting from here, and you can see that the model will go to the minimum. It's a global minimum here, and it will perform it well. Now if I increase, again, the sensitivity of parameter h, and I keep the sensitivity of the parameter y the same, and I use the same learning rate, now we are seeing this behavior where, because the learning rate is too high for the x-axis, it bounces from one side to the other side, but still it will converge. At one point it will get here, and then it will converge here. And instead of converging in 14 steps, now it takes 140 updates to converge. And it's still the same algorithm with the same learning rate. And the worst case is that now I have this parameter that is 10 times more sensitive than this parameter, and the model does not converge anymore. We can see that the loss here will be stuck here, because the learning rate is too high, and now the direction would just bring me on the other side, and again from this side I will go to exactly to the same point on the other side. So I'm just moving around, and there is no improvement. So gradient descent is not an algorithm that will work for any possible function. It doesn't even work for quadratic function if I keep the learning rate constant. So one solution is to divide the learning rate by 0.01. If the gradient are if the direction is too long, I just have to decrease this the length of this direction. So I will use a learning rate that I will divide by 10, 0.01. And this is the dynamic I will have, the learning dynamic. So at the beginning, it will be relatively fast. But as soon as I arrive in this, on the axis of y, it's super slow to converge. But at least I will converge to the global minimum. So this learning rate seems to work well on this direction, but it's too small for this direction. And how can we quantify the problem? This is related to a quantity called the condition number. So the condition number is the ratio of the absolute value of the largest eigenvalue divided by the smallest eigenvalue. Here I will not review what is an eigenvalue. So an eigenvalue is related to the axis of the ellipse. It's not, so if I turn the ellipse in some direction, the alien value will be the measure on the axis of the ellipse and not on the axis of my parameter space. But here, since the ellipses are aligned with the parameter space, because I have a diagonal matrix, the transition number is only 10/1. So what we want to do is usually have a transition number which is close to 1. It's not, here we can see that a transition number of 10 is not good for gradient descent. So what is not working in this algorithm? In fact, it's this learning rate, this eta. And if you look at the physical units of this equation, here I'm receiving two parameters, the parameters x1, x2. It's replaced by the old value of these two parameters, minus eta, and then I have the gradient for the first parameter and the gradient with respect to the second parameter. The parameters can live in, maybe here the function will take a length, expressed for the first feature as kilometer, for the second features as millimeter, and the gradient, the function will map it to some energy metric, like a joule. And here the first partial derivative, the units will be joule over kilometers, and the second one will be joule over millimeters. And so how can I convert this quantity to have the same physical units as these two quantities to obtain kilometers and millimeters? If eta has no physical units, then I'm adding things that are completely different in terms of physical units. They are not the same thing at all. So eta must convert the units of these two quantities into something that is compatible for these two quantities. It's only physical units. I'm just studying the physical units of this algorithm. And to do so, I can just add one matrix in front of my gradient that I will name MT. And I will take it as a diagonal matrix because it's enough to have the good physical units. M11, I will interpret it to be kilometers squared per joule. And M22 will be millimeters squared per joule. And if I multiply this one with this one, the joule will cancel out. The square will be removed by the denominator here. And I retrieve kilometers for the first and millimeters for the second one. So at least I need this matrix in front of my gradient so that this gradient equation will make sense. Otherwise, my naive implementation of gradient descent was not making sense in terms of physical units. I need this matrix in front that will rescale my gradient in a proper way.